Hey guys, uh, just want to throw together sort of a quick EKG review for you. I know for many of you this is your first time dealing with EKGs, and although I think the material in the physiology class is good, I think some of it's at a little bit higher of a level. So we're going to try to break it down into a little bit more digestible material and hopefully simplify it for you. And hopefully this will give you a better understanding of how EKGs work. I'm going to use this PowerPoint that I'll put it upload to, or I'll upload it to Facebook so everyone can have it. And I'm going to be clicking back and forth to some other stuff that I can draw on to help illustrate my point. Now, the PowerPoint I made for the cardiology class for interpreting 12 leads, so there's a lot of material in there that is out of scope of what we're going to cover today. So just stick to the slides that we go over today. And if you have any questions, feel free to contact me and I'll help you as best I can. First, I want to start with everyone's favorite, the awesome cardiac action potentials. So, there's only a few cells that we're really concerned about from an electrophysiology standpoint in the heart. And you have the myocytes, which are the muscle cells, and you have ones in the ventricle and ones in the atrium. They act pretty similar to each other, but there are a few differences. The big thing with the muscle cells is they are relying on some sort of signal to stimulate their action potential. Once that happens, they go into phase zero very quickly. They have a strong response. You'll notice that the ventricles have a longer phase two than the atria do. It's because the muscle is thicker and has to work harder to pump all the blood out into the body. So it gives it more time for a longer and stronger contraction. Whereas the atria, its main job is really just to squeeze a smaller amount of blood from the atria into the ventricles. So it doesn't need quite as long of a phase two. Now, there's another cell that's not on here, and those are the cells in the heart that don't conduct electricity. You have like your cardiac skeleton, which makes up the valves that separate the atria from the ventricles, but they also, it's important that they don't conduct electricity because they serve as an insulator and don't allow the signal to transfer down the exterior wall of the heart from the atria to the ventricles. They have to follow this very specific conduction pathway. Now, within the conduction pathway is a group of specialized cells, and these are very different. These are the cells that have that funny current. And if you remember the funny current, it gradually starts to slightly depolarize until it triggers an action potential. Now, here it has listed the SA node, but it's not just one cell in the heart that does this. It's not one cluster of cells. There's actually a network of cells in a very specific pathway that function the same as this. The only difference really between them is their intrinsic rate. And what I mean by that is the slope of phase 4 gets more gradual or less steep as you proceed down the heart. That allows these other areas to serve as backup pacemakers in the event that the SA node fails or the area above it fails to propagate a signal on its own. So, for example, here you can see phase 4 in the SA node. In the AV node, you'd probably have something very similar, but it would just be a more gradual time that it took to reach that depolarization or to cause that action potential. So, each of these areas has its own intrinsic rate. So, the SA node normally fires between 60 and 100 beats per minute. And then there are other places in the heart where it fires slower, and I'll get into those in just a minute. But I want to review that electrical pathway, and we can look at how the combination of the electrical signal following the right path affects the contraction of the heart in the right order that we want for efficient cardiac pumping. So there's two concepts that you need to understand with these cells. The first is automaticity, which is pretty simple, and if you can understand how this works, you kind of got it. If you're struggling with it, it's basically most of the muscle cells, like the muscles in your arms or legs, require an input from your nerves to trigger those muscles to contract or relax. Those cardiac cells have automaticity where they function completely independent of the nervous system. Now, the autonomics can mediate them and speed up or slow the heart rate as needed, but they don't have complete control over them. They will still eventually reach an action potential on their own. That's why someone can be brain dead and still have a pulse. Or someone who completely severs their spinal cord, their heart will still beat, even though the autonomics won't be able to control it as well anymore. Excuse me. The other concept that's important is this thing called syncytium. You don't have to remember the word, just understand it. It has to do with the way that the cardiac cells are interconnected through gap junctions, and those electrical signals can immediately propagate from one to another. So I like to think of it like ripples in a pond. If you threw a rock in water, when that one cell fires, it will spread that action potential to all the neighboring cells, which will spread it to their neighboring cells, and it'll just move out in all directions, the same as ripples would. And those are two very key concepts in understanding how this electrical signal gets passed through the heart. So let's take a look at the pathway. Like I said, it's not just one cell or one bunch of cells. You have this network of those special cells that have that automaticity, but they all have different intrinsic rates in them. So instead of just having one pacemaker, you actually have a bunch of pacemakers throughout your heart, but you have one that's in the lead, and that's your SA node. In a normal, healthy heart, your SA node is where your heartbeat signal is supposed to start from. It'll follow down this pathway through the atria, and then because we have that cardiac skeleton here that doesn't let the impulse through, it has to go through the AV node. Now I'm going to switch to another view of it, which I think will give you a slightly better view of things. So this doesn't show like Bachman's bundle or the nodal pathways through the atria, but it gives you a much better picture of what goes on in the ventricles when it gets below there. So remember, this electrical signal also stimulates contraction of the heart, and it's very important that it follows this specific path, because the contraction has to take place in a very specific way to efficiently deliver blood to the body. So my impulse is going to start from my SA node. It's going to travel over and down here. And because I have that cardiac skeleton here, which is essentially going to act as a huge insulator, it's not going to allow that electrical signal to just transmit straight down the wall of the atria into the wall of the ventricle. That's very important. I don't want the muscle to start contracting here and then start contracting here. I want the atria to contract from the top down to squeeze blood into the ventricles, and then I want the ventricles to contract from the bottom up to squeeze blood out the valves to the aorta and the pulmonary artery. So when my signal first starts here, that's going to trigger these muscle cells near the top of the heart to start to contract, and they're going to squeeze blood down into the ventricles. That signal can't go anywhere, so it's going to go to the AV node. Now the AV node is unique. The signal slows down dramatically as it goes through the AV node, and there's a very specific reason for this. If you remember Starling's law, when the heart is more expanded, it will contract with greater force. So I get a phenomenon that's called atrial kick, where basically the heart fills during diastole when it's at rest. So right before this heart gets ready to beat, most of these chambers should be almost completely filled with blood. But what I'm going to get is these atria are going to contract, and they're going to squeeze that extra bit of blood down here into the ventricle and just engorge it more, so that it will be able to contract with more force. So that delay through the AV node is important in that it gives time for the atria to contract and squeeze that extra bit of blood into these ventricles, so I get better cardiac output to the body. So that's why I have a delay through the AV node. Now once it comes out of the AV node and goes down here into the bundle of His, the signal is going to be transmitted much, much faster. And basically it's going to rocket down here through the septum. It's going to split into the right and left bundle branches and go down to the apex of the heart. Then it's going to come around the outside walls and up the exterior of the heart. At the same time, it's also going to stimulate the papillary muscles, which are going to close the valve separating the atria and the ventricles, so that I don't get backflow of blood into the atria. It's really important to be able to understand why it has to follow this pathway, and that deviations from this pathway can cause significant problems with the cardiac output or physical contraction of the heart. So if you can kind of wrap your head around how that ties in with what the heart is doing, it becomes a lot easier to understand and then sort of interpret the EKGs and figure out how serious of a problem you have and where your problem is. So remember too that these all have different intrinsic rates, and basically that's back to that slope of phase 4. So your SA node should normally fire between 60 and 100 beats a minute. From the AV node to around the bottom of the bundle of His is usually anywhere from 40 to 60 beats a minute, and then anything down here is usually less than 40. I have a table here in the PowerPoint that has a lot of numbers on it. Don't get wrapped up in those. That's just a guideline, but they're there if you need to look them over. The best way I can explain this is it's essentially like a backup system. So your SA node, and I'll put this in football terms, think of your SA node as your starting quarterback. If something goes wrong and your SA node fails, then you have a backup quarterback. So the next one would basically probably be your AV node. So if it hasn't received a signal fast enough from the SA node, it will eventually reach its threshold and activate its own action potential. Granted, it'll be at a slower rate. So if your first string quarterback gets hurt, it doesn't mean you're out of the game. But the further down your depth chart you have to go, the worse off you are. Like if your AV node and SA node both get taken out and you're relying on the intrinsic rate of the ventricles, you're going to have a heart rate probably in the 30s. You may still live long enough to make it to the cath lab, but you're not having a good day. So let's take a look at what it is that an EKG actually does. Essentially, all I'm going to do is take a couple of wires and attach them to a patient. Now, when I have 2 wires attached to someone, I call that a lead. Usually, in the hospital, you'll hear people call the individual wires leads, but the lead is actually a term for the point of view that you're looking at the heart. So you take these little stickers that have an electroconductive gel on them, and you stick them on the patient. So you're going to have one little sticker attached to a wire that goes back to your heart monitor, and you're going to have another little sticker attached with a wire that goes back to your heart monitor. One of them is going to be positive, and one of them is going to be negative. Now, all these do is they measure electrical activity between these 2 wires. So if I have electrical activity that's traveling towards my positive wire, or towards my negative wire, that's going to cause a deflection on my graph. Now, if I just connect these wires to anything that conducts electricity, but there's no electrical stimulus, then I'm going to get essentially this, which is also called asystole. I could hook 2 electrodes up to a cadaver in the anatomy lab, and you would get asystole because there's no electrical activity going on in the heart. So congratulations, now you know how to interpret your first EKG rhythm. Now if I throw a beating heart into the mix here, any of that electrical signal that travels towards the positive electrode is going to cause a deflection upwards. And anything that travels towards the negative electrode is going to cause a deflection downwards. Now because this does this in real time, it can't move 2 directions at the same time. So basically the machine interprets how much of it's going this way, how much of it's going that way, and gives you a net output. So if I had 90% of it going towards the positive electrode and 10% of it going away from the positive electrode towards the negative, then I would get a net of somewhere around here. Another important thing to remember with this is that if I have an electrical signal that's moving completely perpendicular to the electrodes, it's not getting closer to either one. So it won't read anything at all for any signal that's moving perpendicular to it. Another thing is, if I have equal amounts going this way and this way at the same time, they cancel each other out. So both of those would result in just a flat line. Now, I have to throw a little bit of physics in here because I know everyone loves physics so much. but it's a fairly simple concept. If you remember, you probably had a bunch of questions where there was like a box on a table and you had to move the box with a force. So you could move it this way, or you could push straight down on it this way. But they always gave you complicated ones where you were pushing it at an angle like this. So if you remember, any kind of vector or force moving this direction has a component of it that's going down and a component of it that's going this direction. So if I push this direction on the box will still move this way, but not as much as if I was pushing straight this way. So the same thing happens with the electrocardiogram. You're going to have impulses that move this way, and this way, and this way, and this way. And it's basically going to figure out which parts of this are pointing towards this direction and ignore the ones that are moving in this direction. So I'm going to get this big net total of all of these together at one time. And that's going to give me either my positive or negative deflections on the graph. Now the way this works is actually very simple. Inside the machine there's a piece of paper and there is a little pen on it. And the pen either moves up or down depending on the information that it gets from the wires. And the paper gets fed out at a constant speed. So then what I could do is measure this electrical activity over time. And it's a standard set of measurements, and we'll get into that a little bit when it comes to determining rate. But I'll show you very quickly. The way the paper works, it's just this little graph paper. This is standard EKG paper. And the paper moves at 25 millimeters a second. So each one of these little tiny boxes is a millimeter. This will vary depending on manufacturer, but everyone makes slightly different EKG paper. But usually all the small boxes are here, and then these are broken down into 5x5 squares. Sometimes you'll have a mark here that's every second. Not always. Sometimes you'll get another mark that's bigger for every 3 seconds, but not always. So when you start looking at rate, you look at how far apart the R to R waves are. We'll get into that soon. But just know that it feeds out at 25 millimeters a second. So okay, now that I have all this, how does this translate into taking an EKG on a patient? Well, in a shout out to Dr. Throckmorton here, we'll use our Vitruvian Homer Simpson to kind of demonstrate how we're going to do this. So essentially, I want to take different views of the heart to be able to look at it from different angles. Try to imagine if someone tells you, hey, there's a dent in your car. You go out and you look at your car from straight on. If there's a dent in the back of it, you won't be able to see it. So I want to be able to look at the heart from different angles to see all the different sides of it. So the first 3 leads that we usually look at are lead 1, lead 2, and lead 3. So we'll do lead 1. All right, so I'm going to put my little electrodes on Vitruvian Homer here. So we're going to put an electrode on the right hand, the left hand, really the wrist, and the left leg. And then I'm going to be able to look at the heart from 3 different angles, usually these 3 leads. So in lead 1, I'm going to make this my negative electrode, and this my positive electrode. In lead 2, this one stays negative, and I make this my positive electrode. And then in lead 3, this stays positive, and I move my negative over to here. So when I look at the 3 of these together, what I essentially get is a view like this, and like this, which gives me a nice triangular view of a of the heart from 3 different angles. Now, this is called Einthoven's triangle. And here is a slightly fancier drawing of it. It gives you an idea. Now, if you remember, I erased that one. If you remember, the machine can't pick up views that are perpendicular or any electricity that's traveling perpendicular to these leads. So someone came up with a bright idea of developing leads that were perpendicular to these without having to move all the wires. So with the computer, what they can basically do is they can leave this positive, make this negative, and this negative, and sort of combine the two together. And that gives you a view that is basically straight up and down. So these are called your augmented leads. And you'll hear variations, either augmented voltage or augmented view. I find them easier to remember if it's augmented view. If I make both of these negative, all my augmented view leads start with AV, and then there's AVR, AVL, AVF. If you just remember where the positive electrode is, in AVF it's at the feet, in AVR the positive is on the right arm, and in AVL the positive is on the left arm. So here's a slightly more descriptive picture that'll show you how those work. So you can see here's one, and then its perpendicular one is AVF, where I combine both the negatives here. 2 with AVL, 3 with AVR. Now, there's a reason I also like the Vitruvian Man. If you remember the shape here, you kind of have an X and a cross in the middle. When you look at a 12-lead EKG, the first 6 leads on it are 1, 2, 3, AVR, AVL, and AVF. But they don't put each one next to the one that it is opposite. But if you can remember that shape of the Vitruvian Man, that'll help you remember which leads are perpendicular to each other. 1 is perpendicular to AVF, 3 to AVR, and 2 to AVL. So we'll get back to those in a minute when we start talking about trying to figure out cardiac access, pardon me. But I want to talk a little bit more about how we interpret these lines when it comes to knowing what the heart is doing. So if we go back to our conduction system, let's pretend we're in lead 2. So if we're in lead 2, our negative is up here, and our positive is down here. Now, when my SA node fires, which is the way a normal heartbeat should begin, this electrical signal is going to propagate in this direction, a lot like those ripples, and it's going to travel mostly to the left and mostly down. Now, since the AV node is up near the very top of the right atrium, I really shouldn't have any energy moving towards the negative electrode. It's all either moving to the left or towards the positive electrode. So as this occurs, I shouldn't have any negative deflection. So I'm going to get this nice upright P wave here. And that shows, it doesn't show the contraction, this only shows the electrical activity in the heart. So this shows that electrical signal being transferred through the atria. Now when I hit the AV node and things slow down, I'm going to get a little bit of a pause. There's a delay while I wait for those atria to contract and fill the ventricles with blood. And that delay is going to be right here. And since there's no more significant electrical activity happening, it doesn't really get picked up. So I get a nice little flat area here, and this is my PR segment. And that's just the area in between my P wave and the start of my QRS. Now, the way we measure this is called the PR interval. The PR interval is only from the beginning of the P wave to the beginning of the QRS complex. And in a normal, healthy heart, that should take anywhere between 0.12 and 0.20 seconds. So when we go back to our EKG here, that should be between 3 and 5 of these little boxes. If it's longer than that, there's a problem. If it's shorter than that, there's a problem. But we'll get into that later. So now I get my delay. My delay's over, and I'm going to come through down to the bundle of His, and now this signal is very rapidly being transmitted here. And because the ventricle is so much larger and much more dense, there are a ton more electrical signals happening here. There's a lot more action potentials, a lot more cells are being activated and depolarized. So I get a much bigger output, typically, depending on the view I'm in, for my ventricular depolarization. So since most all of this is rocketing this way, almost in line with my positive electrode, I'm going to get a very quick and steep upstroke, and that's going to be my R wave. Then as that signal goes around and goes up the outside of the heart, it's going to travel in the opposite direction and come back down and give me an S wave. As this depolarization finishes, my EKG should normalize and go back to my isoelectric line, which is the same as that asystole line. There's no real significant electrical activity happening anymore. But remember, my ventricles are still in that phase 2, that prolonged contraction, to make sure they're squeezing good and hard. Then as they start to relax, they're going to repolarize. And as they repolarize, that's where I'm going to get my T wave. And this is just showing repolarization of the heart. It doesn't happen with as much velocity or as much force, so it's not as dramatic of a wave. It should be smoother and should almost always be upright. There are times where those will get flipped over, but we'll talk about that later. Excuse me. So if you can kind of understand what each of these things is representing, then it becomes easier to read your little roadmap. So I want to show you a 12 lead of a normal sinus rhythm. And you can see that I have all these different angles that I'm looking at the heart. Now AVR is an anomaly. Everything in AVR is supposed to be upside down. So if that one jumps out because the P waves are upside down and everything's negative, and the T waves are upside down, it's supposed to be, don't worry. But in the rest of my leads, I have a nice upright P wave, I have a very narrow QRS complex, which I should, and I have a nice upright T wave. And that's consistent through the whole thing. Now in some views I may not be able to see the P wave as well, like in AVL it's very difficult to discern the P wave, and in V4 it's very hard to see. The more you look at them, the better you'll get at being able to find these different things. Sometimes they're more subtle than others. But don't memorize just this picture, because not everyone's EKG will look exactly like this. There's significant variation from person to person. But each of these events should be happening. Now the other one I don't think I touched on was the width of your QRS complex. If your QRS is traveling down the correct pathway, this should take less than 0.12 seconds. So your QRS should be narrower than 3 of these little boxes from start to finish. You can see this one is really 1.5, maybe 2, but it shouldn't be more than 3. If it's more than 3, then it's usually not following the right conduction pathway, and that can happen for various reasons. And I'll touch on this a little more when we go over EKG rhythms, but first I want to get into axis deviation, because that's one that seems to haunt people, and it's really not as confusing as it sounds. So basically, when I'm trying to determine my cardiac axis, and I'm a terrible drawer, so I basically draw hearts like this. But when I'm trying to determine axis, I'm just looking for the average direction that the electrical impulse is traveling. Now remember that your heart sits in your body, it's not straight up and down, it sits at a little bit of an angle. But there's variation from person to person for exactly what angle your heart should be at. For example, if a woman gets pregnant, she gets a lot of pressure in her abdomen that pushes up on her diaphragm and pushes up on the heart, and will actually shift the heart. It'll rotate and push the apex more to the left. If you have someone who's tall and very thin, a lot of times their heart is kind of hanging down a little bit more, and the axis shifts a little bit to the right, literally because the heart is physically moved out of the conventional position. But other things that are important for determining axis are a lot of disease processes. So if I'm trying to figure out the sum of all of these vectors that are coming down and going away as depolarization happens, I'm really concerned with the ventricles. So I'm looking at only my QRS complex to determine axis. So for example, if someone develops left ventricular hypertrophy, they have untreated high blood pressure for years, and their left ventricle becomes bigger and thicker, I'm going to have a lot more electrical activity pulling in this direction. Much more so than it's pulling over here. And that's going to shift my axis from maybe this point to one this angle. If it gets really severe, it can be significantly off. I may have a ton of energy coming back up this direction, and eventually that can give me a left axis deviation. Now, if we go back to our chest leads, you can remember we had 1, 2, 3, and then the perpendicular leads, AVR, AVL, and AVF. If you look at the different theoretical angles that those are looking at the heart, and this is a much better picture, I think, than the one that is in your lecture PowerPoint. This basically explains the angles of each one of these leads and how they view. So here's 1, 2, and 3. Here's AVR, AVL, AVF. And when you combine them together, you get this little circle here. Now, there is variation depending on which book you look at for what is a normal cardiac access. I would stick to what Dr. Fitzovich told you, especially since he's writing your exam. And it's -30 to -110 degrees is considered normal. So just remember, as you go across this way, this is 0. And as you go clockwise, things get positive. So it's +30. And so on and so on and so on. But your main leads are at 60 degrees is going to be lead 2. At 120 degrees is going to be lead 3. And then as you go this way, they become negative. So this is -30. -90. And so on. So this looks very confusing and complicated, but the most simple system that you can use is the quadrant system. And I know for Dr. Fitzovich's exam, or at least in his lecture, he mentioned that the vector system can be time consuming. Also, if you're really bad at drawing graphs, it's kind of inaccurate. There's other ways that are better at determining it, but for basic purposes, the quadrant system works very well to try to figure that out. So the gist of this is you draw a circle. Now I know that lead 1 is looking this way from negative over here to positive over here. And AVF is looking this way, positive here and negative here. So if I look at my EKG, let me bring that 12 lead back up again here. If I look at my EKG, I look at lead 1 and I look at lead AVF. And I'm trying to figure out the net result. Is it more positive or more negative? So for example, we'll look at a different lead here real quick to understand. If you look at V4, the QRS complex goes up 5, 10, 15, close to 20 millimeters, and goes down probably 3. So if I take the 18 that go up and subtract the 3 that go down, I have a positive of about 15. So that's very, very positive. Now, for the vector method, you would want to figure those out. For the quadrant method, you're just looking at overall, is it more positive or more negative? Now, sometimes it can be difficult to tell. Like if you look at V2 here, it's almost equal positive and negative. But in most cases, you'll be able to determine from lead 1 and lead AVF, whether they are more positive or more negative than the other. So if we go back to our little quadrant here, if I know that lead 1 is positive, lead 1 is here, then I'm in the positive side on lead 1. And then if I know that AVF is also positive, wherever these two overlap, whichever quadrant they're both covering, I know my axis falls within that quadrant. It doesn't give me a specific number. It's a very general term. So it's not 100% foolproof, because remember, my normal axis also goes to negative 30 degrees here. So there can be times where AVF is negative and lead 1 is positive, and I still have a normal axis, because it may be right in this area if I sat down and did the math. But I think for exam purposes, and at this level, I think it's a safe bet to use a quadrant system. If you want to use the vector system, having gone through this, maybe the vector system will make a little more sense to you. I don't really want to explain it because I can't draw it very well, and I don't like it. But I want to show you a way that I found that I think is a lot easier to understand the quadrant system without having to draw circles and figure out and shading things in. It's much faster, much simpler. I know someone was teaching another way to do it last year, so if you know another way, just ignore this part because it might confuse you. But the way I learned it is extremely simple. Just look at your thumbs. All right? Most everybody is right-handed, and I know this sounds corny, but bear with me. Most everybody is right-handed. So your right thumb is your number one guy. That is your right-hand man. Make that lead 1. The opposite of lead 1, the opposite of your right hand, is going to be AVF. So if I look at lead 1 and look at AVF, I figure out which one's positive, which one's more negative, and I move my thumb in that direction. So let me pull up another 12 lead here. And we'll look at a right axis deviation. Or actually, you know what? We'll go with the normal one real quick. Okay, I look at lead 1, that's my right thumb. I look at AVF, it's more positive, that's my left thumb. I have 2 thumbs up. 2 thumbs up means everything is great. I have a normal cardiac axis. I know it sounds like crap, but it really works. So let's look at a different one. Here I have a right axis deviation. I look at lead 1. Lead 1 is more negative than it is positive. So I'm going to turn my right thumb down. I look at AVF. AVF is more positive. So I have right thumb down, left thumb up. Whichever thumb is down is pointing towards my deviation. So I have a right axis deviation. If I have a left axis deviation, my right hand thumb is up because lead 1 is more positive. AVF is turned down. So my left thumb is turned down. I have a left axis deviation. Now, if for some reason both thumbs are pointing down, just like watching a crappy movie, that means it's really, really bad. That means you have an extreme right axis deviation. Those are very rare. That usually means that it's a ventricular impulse that's carrying over the signal, and it's moving from the bottom of the heart to the top of the heart. You see it more with pacemakers or someone who's in like ventricular tachycardia. It's not something you're going to run across very often. But if you can remember that rule of thumbs for the axis deviation, you shouldn't have any trouble, and that should get you through this part of EKGs just fine. So I'm going to take a break here with this one, and then I'll come back with part 2. We'll go over the different determining rate, look at some of the basic rhythms that you guys learned in physiology, and talk about the Q wave progression. So hope to help. If you have any questions, feel free to hit me up on Facebook.